Okay, so in the previous few slides, we have already discussed what is the effect of pool to the behavior of the system. We briefly discussed that if we have a positive pool, we will have an unstable system because the response of our system will go to infinite value. But when the pool is negative, we will have a stable system because the response will always converge to one particular value. But we have also discussed in the previous few slides that pool can also be complex number. So in this next few slides, I will discuss what is the effect of the location of the pool. What is the effect of the number of the pool, either if it is real or complex, to the response of the system, to the stability of the system. Before we discuss the effect of pole location to the system behavior, let me introduce this S-plane to you first. What is S-plane? So basically what you see in this slide, I have a plane in 2 dimension where the horizontal axis represent the real number of your pole and the vertical axis represent the imaginary part of your pole. So let's say you have a pole which is equal to 3, real number 3. So in S plane you will represent it as you can see in the slide. You can just draw the pole at this location. If you have another pole which is complex, let's say, and your pole is equal to 2 plus j, you will draw it at the location that is shown in the slide also. Or another example, you might have another pole which is equal to negative 3 plus 2j. You can draw it also at that corresponding location. Now, once we discuss S-plane, we can discuss on how is the effect of this pole location to the stability of the system. In this slide, you can see what we call as a pole location map. This map will tell you how the system will behave if you have different location of your poles. So the horizontal axis again is the same. This is a nice plane. The horizontal axis is the real number of your pole, and the vertical one is the imaginary axis. Those area on the left side of the imaginary axis, I will call it as a left hand plane, and those in the right of the imaginary axis is the right hand plane. Okay, what you can see from this map is that, let's take one example. If you have a system and the system has a negative real pole at that location, the response of your system is presented by this figure, which means the response of your system will converge to one particular value and the response is not oscillating. That is to say, then, if you have a negative real pole, your system will be stable and there won't be any oscillation on it. On the contrary, if you have positive real pole like this one, then your system will respond like this. Again, there is no oscillation that we see in this map, but your response is going to infinity. So in this case, if you have positive real pole, you will have unstable system. How if we have a complex pole? Let's say you have a complex pole, but the real part of your pole of this complex pole is negative. So as it is represented by this pole, let's say, this means the real part of that pole is negative. In this case, if you have a complex pole where the real part is negative, your response will always oscillate. But the amplitude is getting smaller, smaller, and smaller until after sometimes it converges to one particular value. So in this case, even though the response is oscillating, but your system is stable because the response will go to one particular value. Now let's consider another case when you have a complex pole in your system again, but the real part of that complex pole is on the right hand plane, which means the real part is positive. The response of that system with that particular kind of pole is oscillating, but the amplitude is growing. The amplitude is getting bigger, bigger, and bigger, which means your system is also unstable in this case. So looking at this pole location map, we can conclude easily that any poles on the left hand plane is a stable system. But if your system has poles on the right hand plane, saying that the real part of the pole of your system is positive, your system is unstable. What happens if you have it in between? In between means you don't have real part in your pole. Your real part is zero. That means if you represent it in the S plane, your pole are located at the imaginary axis. If you have this case, then your system is marginally stable. The response is not converging to one particular value, but the response is also not growing to infinity. It's not stable nor unstable. So this is what we call as marginally stable system. Let's take more example on this pole location map. So let's consider I have a system where the transfer function is gs. Gs is equal to 1 over s plus 4. This means my system will have a pole at negative 4. You know how to find the pole, don't you? You just have to find the roots of the denominator, the roots of the characteristic equation. So in this case, the pole is at negative 4. Now let's consider to the system, we give a unit step input. So the input is unit step, which means the input in Laplace domain is equal to 1 over s. And then when you want to evaluate the response, response is always equal to transfer function times the input. So you multiply the transfer function with the input 1 over s. 1 over s is again the unit step signal in Laplace domain. So once you calculate it, you will get this form, and then we do partial fraction expansion, and then you will get this form. After that, you can refer to Laplace table, and then you can transform it back the response to the time domain. You can check it by yourself. After you transform it to time domain, this will be your response. Now let's try to plot this response as a function of time. If you plot it, the response will look like this. So as you can see in here, the response is not oscillating, but in time, the response will converge to one particular value at this point. So in this case, you can conclude again then here, if you have a negative real pole, your response is not oscillating, but your system is stable. Negative real pole, no oscillation, and stable. If you refer back to the pole location map, this is what you will get. You have negative real pole, the response is not oscillating, but the output is converging to one particular value. So this is how you interpret the pole location map. Let's take a look on the second example here. I have another system with different transfer function. Now my transfer function is equal to 1 over s squared plus 4s plus 29. We can identify the poles from here. How to do that? You just factorize the denominator, or you can just simply find the roots of the characteristic equation. Just factorize the denominator. Once you factorize it, you will get these two poles. What do you see in this pole? You have complex conjugate pair of poles where the real part is negative. Now let's try to evaluate this unit step response of this system. Same like before, to get the response, I have to multiply the transfer function with 1 over s. This is the transfer function. This is the input. And then we do the partial fraction expansion. After that, we inverse it back to the time domain. If we plot this response in time domain, we plot ct versus t versus the time, the response will more or less look like this. What do you see now? The response is oscillating, but in time, the response is converging to one single value. This implies that your system is stable, but it has an oscillation. Why do we have an oscillation? You can refer again to the pole location map. In our case here, we have complex conjugate pair of pole with a negative real part. If you refer to the pole location map, the location will be somewhere here. You have complex conjugate pair of pole where the real part is negative. So as what is represented by the map, the response is always oscillating, but the response is always converging to one particular value, saying that the system is stable. The next example, let's take a look on this example. So I have another system again. The transfer function of the system is 1 over s squared plus 4. We can identify the poles of this system again. You just again factorize the denominator. The poles are equal to 2j and negative 2j. That means in this case, you only have imaginary poles, no real part on it. Let's take a look how the system will respond to a unit step input. I multiply the transfer function with the input 1 over s. I do partial fraction expansion and then I inverse Laplace it to the time domain. If I plot the response in time domain, this will be the response. So as you can see from this plot, the response keeps oscillating all the time with the same amplitude. It's not converging to one single value, nor the amplitude is never growing. So in this case, then you don't have stable system, but your system is not unstable either. This is what we call as marginally stable system. Let's refer to the pole location map now. When you have imaginary poles, saying that the real part of your poles is 0 in the map, it will refer to this location. As you can see, if you have imaginary pole, your system is always oscillating, or you can say that the system is marginally stable.